Hello everyone. Now we will discuss production of X-rays. Before we start, first let's see the components of the X-ray machine again. So we know we have an X-ray tube over here, and inside this X-ray tube, X-rays are formed. Once they are formed, they come out through the window over here, and above this we have filter and collimation system over here. Once the X-rays come out, they interact with the matter, and the final attenuated signal is received on the detector system over here. So we have talked about the X-ray tube, and now we will discuss how X-rays are produced inside this X-ray tube. Here we have a typical figure of X-ray tube. In this we can say this is the uh, anode and this is a cathode. We know we have a cathode filament over here, and this cathode filament is heated, and it gives off a cloud of electron by a process known as thermionic emission. And this large electron cloud is accelerated towards the anode because of a potential difference between the cathode and anode, and this potential difference is called as tube potential. And once they go and they hit on the anode, they like electrons are moving, so they have some velocity, and as a function of velocity they will also have kinetic energy. And as these electrons go and hit on the anode, they lose their kinetic energy. 99% of the kinetic energy is converted into heat, while less than 1% of kinetic energy is converted into the X-rays. So here we can see again, this is the copper filament over here. It's heated and it releases a cloud of electrons by a process known as thermionic emission. Then due to tube potential, these electrons are accelerated towards the anode. They hit the anode, and 99% of the kinetic energy is converted to heat, and less than 1% is converted into the X-rays, and they come out through the beryllium window. And at this anode target level, the electrons can interact with the anode atom at the level of outer shell electrons, inner shell electrode, or at the level of nucleus. So if they interact with the outer shell electrons, then most of the process which happens is at outer shell electron, and here we have the production of heat. Whereas if these electrons interact with the inner k shell electrons of the atom, then we have something called as a characteristic radiation. Whereas if they interact with the nucleus, then we have something called as Bremsstrahlung radiation. So ultimately, again, 99% energy is converted into heat, and less than 1% is converted into X-rays, which can be characteristic or Bremsstrahlung X-rays. So like we discussed, we have two types of X-rays. We have Bremsstrahlung or breaking radiation and characteristic radiation. Breaking radiation or Bremsstrahlung is more common. So what happens in it? That on approaching the strongly positive nuclear field of the target atom, this negatively charged high speed electrons are deviated from the initial path because of the attraction between them both, that is the positive charge nucleus and negative charge electron, and this results in a slowing down or deceleration of the electrons, and thereby losing some of its kinetic energy. Here we can see in the figure also, this is a fast moving electron. Due to the positive attraction between them, the electron is deviated from its initial path, and because of deviation of its initial path, it loses some of its kinetic energy, which is radiated in the form of this breaking radiation or Bremsstrahlung radiation. So this lost kinetic energy is radiated as Bremsstrahlung radiation or breaking radiation. So what we can see from here is that this radiation, that is the breaking radiation or Bremsstrahlung radiation, it depends on the angle of scatter. That is how much the X-ray electron has deviated from its normal path. And so, depending on this angle of scatter, we can have a continuous spectrum of the Bremsstrahlung radiation from very low energy to very high energy also. And this is represented by this X-ray spectrum graph over here. This X-ray spectrum graph is the graph between the photon number and photon energy. And if we plot photon number versus energy, and we can see Bremsstrahlung radiation like this, that we can see maximum of the X-rays, Bremsstrahlung X-rays are low energy photons, and mostly they are low energy photons, and very less are high energy photons. What happens is they interact, and if they are away from the nucleus, they will deviate very less, and most of them are away from the nucleus, and more closer they are, they will deviate more and they will have higher energy. But the electrons which are near the nucleus will be less, and the electrons which are away from the nucleus will be more. So ultimately we will have more towards the low energy spectrum and very less towards the very high energy spectrum. So that is a Bremsstrahlung radiation X-ray spectrum. So this was Bremsstrahlung. Second, coming to the characteristic radiation. Before coming to that, I should also cover the concept of filter. So like I've showed you just now that this Bremsstrahlung radiation, we have most of the photons in the low energy spectrum, and the problem with that is this low energy photons means that they will go interact with the surface of the atom or body, and will attenuate there only, and they will not have any role in image production. They will not have any significant role in image production. So ultimately they will just cause surface radiation exposure and will not have any role in image formation, and we don't want that because it will be unnecessary exposure to the patient. So what we do is we put filter over this, and the importance of this filter is this will attenuate or this will absorb all the low energy photons. So ultimately our X-ray spectrum will be something like this. The most of the photons will be in the middle range, and very less photons will be in the low energy range, and very less in the high energy range. So that's the X-ray spectrum of the Bremsstrahlung radiation, which is after filtration. Now coming to the characteristic radiation. So Bremsstrahlung radiation was because of interaction of this fast moving negatively charged electron with the interaction with the positive nucleus. But if this fast moving negatively charged electron interacts with the case shell electron, so what will happen? It will interact with the inner orbital or case shell electron, and it will eject this electron from its orbit, creating a hole or a vacancy, and which vacancy is filled by a electron which is transitioned from one of the outer shells. So like in this example you can see this is the case shell, and this is the free electron, this is the electron. So our free electron came, it hit interacted with this case shell electron, and it causes the case shell electron to come out, and so there is a hole in this case shell. To cover up this hole, one of the electron of the outer shell will come and take its place, and once it come and take its place, it will lose some of its energy, and this loss of energy is radiated in the form of characteristic radiation. So as we know, this loss of energy will be equal to the energy of the K shell and the L shell. So ultimately it depends on the binding energy of the K shell and L shell. So this is not a continuous spectrum. This will be of some specific values which will depend on the K shell L shell binding energy, and their binding energy depends on what kind of target we use. So here it depends on the difference in the binding energy. Like here we can see this was a K alpha. K alpha means that after the K shell vacancy was created, a electron from the L shell came and took its place, and that G characteristic spectrum is called as K alpha. So what will the value of this K alpha? It will be the value. It will be this difference between the binding energy of K shell minus binding energy of the L shell. Binding energy of K shell is 69.5 kilo electron volt, whereas binding energy of L shell is approximately 11.5. So it K alpha will come around somewhere around 58 kilo electron volts. So K alpha is like this. What is K beta? K beta is the hole created or the vacancy created in the K shell is not filled by L shell but from electron from the M shell. So that will be K beta. If it's from L, then it's K alpha. If it's from M, then it's K beta. Now I guess you have understood this. So let's recall this. So we have characteristic radiation, we have Bremsstrahlung radiation, accounts for X-ray production. So we know most of the X-rays are produced in the Bremsstrahlung radiation, and very less or small percentages by characteristic radiation. Interaction of the bombarding electron. In characteristic radiation, these electrons interact with the inner shell electron, whereas in Bremsstrahlung it will interact with the nucleus. And radiation is released due to, in characteristic radiation is released due to electron dropping from a outer shell electron to inner shell electron, and this dropping of the energy result in formation of this characteristic radiation. Whereas in Bremsstrahlung radiation, there is diversion of this bombarding electron from its initial path, and this result in a loss of kinetic energy, and that comes out in the form of Bremsstrahlung radiation. So energy of the released radiation. So we know characteristic radiation will be very specific energies. They will be K alpha, K beta having specific value depending on the binding energy of the shells. Whereas Bremsstrahlung radiation will be a continuous or a large spectrum. And the X-ray beam depends on. So in characteristic radiation, the X-ray beam depends on the target atom. So like target atom, whereas in Bremsstrahlung it depends on the tube voltage. If we increase the tube voltage, the kinetic energy will increase, and we will have more X-ray beam energies. Here it's a normally in conventional radiography we use tungsten. The major source of X-rays in tungsten is brimstone, whereas in mammo we use mammography, and major source of X-ray in molybdenum is by characteristic X-rays. So X-ray spectrum, I've told you what is X-ray spectrum. This is a graph or a figure which is plotted the X-ray photon numbers and photon energy. And we know that we talked about if it's unfiltered Bremson radiation, it will be something like this. If it's filtered, it will be something like this. Characteristic peak will be something like this. And if we combine them, because we know we will have both characteristic and Bremson, so it will come something like this. So that is the X-ray spectrum of the X-rays which we normally see. And here we can see the maximum photon energy is equivalent to the KVP peak. And if this peak velocity is more than the binding shell energy, then we can also get K alpha and K beta characteristic X-rays also. And this dotted line represent the filtration. Now coming to the concept of quality and quantity. Quality means how good are the X-rays able to penetrate the structures. So how quality is basically ability of the X-rays to penetrate structure. So a good quality X-ray means it will be able to penetrate more. So it will be able to penetrate more because it has more energy. So ultimately we have a X-rays having more photon energy. So this depends on the mean of the curve and is the property of X-rays. So we know photon number over here. So if we have more energy, then it will be able to penetrate more. So we will have a mean will be center mean, and if it's more towards the uh, left side, so it means this side, then it means the quality of the X-rays is more good. Whereas quantity means how many photons are there. So this depends on the photon number, and this is represented by the area under the curve, and ultimately is the property of y-axis. So now we'll talk about what are the various factors that affects the X-ray spectrum. So first coming to filtration. Like I have told you, what does filtration do? It will remove all the low energy X-rays. So if it's removing the X-rays, the photon number will decrease. It will decrease the photon number. If the photon numbers will decrease, then quantity will also decrease. Whereas what about the quality? Quality depends on the ability of penetration, how good are the photon numbers or the mean. Now if we have decreased the photon number, so ultimately we have more number of high energy photons, and we have removed all the low energy photons, so ultimately our mean will shift towards the left. So if we had like this, we previously had a lot of low energy photons, so it was keeping our mean somewhere here, but now we don't have this, so ultimately our mean will come somewhere here. So ultimately our mean will increase, our quality will increase. So ultimately filtration decreases the quantity and increase the quality. Coming to filament current, if we increase the filament current, then we will have more number of electrons present for thermionic emission. That will means that we have increased the quantity of the X-rays, but the quality remains same because all the electrons will be moving on with the same velocity. So if we want to increase the velocity, we can for that we should change the tube current and not filament current or tube potential. So if we increase the tube potential, if we increase the tube potential, we will push more number of electrons with more speed from cathode to anode, and this will cause increase in both quality and quantity of the X-ray beam. Anode target, as the atomic number of the target increases, there's increase in the brainstorm radiation. Therefore, more the quantity of X-ray beams will be there. However, quality remains the same. One more thing, if you have changed the atomic number, then binding shell energy of K shell, L shell has changed. So characteristic radiation is also changed. Last is generator waveform. So if we use a high frequency waveform having very low KVP ripple, then KVP is constantly higher for more time, and that means that our quantity and quality both will increase. But we should know that quality will increase not because the ultimate KVP has increased. The quality will increase because our mean average energy has increased, and maximum energy is not changed, or maximum KVP is not changed. Now when we have finished this, let's revise once. So these are true and false statements. You just go them with me. So the collision of electrons with tungsten target mainly produces X-ray. Is this true or false? So we know it's a false statement because it mainly produces heat and very less than 1% produces X-rays. The kinetic energy of electrons in the X-ray tube is equal to the potential difference between the anode and cathode of the X-ray tube. That is a true statement. Free electron with 17 keV is able to dislodge electron from K shell of tungsten target. This will be a true statement because binding energy of K shell of tungsten target is 69.5 kilo electron volt. So if our electron has 70 kilo electron volt energy, then it will be able to dislodge the electron as it's more than the binding energy. If a hole in K shell is filled by electron from L shell, this X-ray photon release is called as breaking radiation, that is K alpha. So if a hole in K shell is filled by electron from L shell, so K to L, this will be K alpha, that is true. But this is not breaking radiation, this will be characteristic radiation. K alpha normally is 58 kilo electron volt for tungsten target, that is a true statement. We have talked about this. K shell binding energy is 69.5 approximately, and L shell binding energy is 11.5. This comes out to be 58 kilo electron volt, that's a true statement. The majority of X-rays in conventional radiography are due to characteristic radiation. That is a false statement. It is due to breaking radiation. The X-ray spectrum is continuous due to breaking radiation. The X-ray spectrum is continuous due to breaking radiation. That is a true statement. So next, Bremson radiation occurs due to interaction of free electron with orbital electron of the target. Bremson radiation is not due to interaction of free electron with the orbital electron. Bremson radiation is due to interaction of the free electron with the nucleus, and this, if it's interacting with the inner orbital, then that will be characteristic radiation. This is a false statement. The highest energy X-ray photon leaving the X-ray tube depend on the KVP. That is a true statement. The lowest energy X-ray photon leaving the X-ray tube depend on the filtration. That is also a true statement. Again, let's revise this. So factors affecting the X-ray spectrum. Filament current. If we increase the filament current, we have more number of electrons available, but the speed will remain same. That is, the quantity will increase, quality will remain same. Whereas if we increase the potential difference, if we increase the tube potential, then we have more number of electrons coming and more faster pace. So quantity and quality both will increase. Whereas if we, after filtration, we know the low photon energy electrons will be absorbed, so quantity will decrease but quality will increase. Whereas if we increase the anode target number, atomic number of target, then the quantity of X-rays will increase, whereas quality will remain same. And coming to generator waveform, if we use a low kVp ripple, high frequency generator, then the quantity and quality both will increase. Thank you very much.